different sections. You might go, oh yeah, that stuff. I don't understand that shit. Let me ask a question about that. So again, if you have all your formula sheets and you didn't lose any points on any of them, you can just bring all your formula sheets on the day of the final. I don't care how many that is. Somebody once asked, have you ever had an instructor let you write notes for a test, but they had to be on a little note card? Have you ever had that? I always joked that some would say you can write it, but it has to be on a grain of rice. So everybody would bring a magnifying glass. It's just stupid. I'm like, you can bring as big of a freaking piece of paper as you want. I don't give a shit, as long as it doesn't bother anybody else, and as long as you just have the formulas that it said you could have, right? So, this will be a little walk down memory lane. You've got chapter 1, which had all the definitions, which was really exciting. Remember those days? Oh yeah, nominal, ordinal, integral ratio, all that kind of business. So there's no formulas in chapter 1 really. Chapter 2, I wouldn't even write this down, but just to remind you guys, this is where we did stuff like this. Remember this formula here? And then there's one for S with the n-1 on the bottom because it's just a sample. It's a little adjustment because it was just a sample. Why do I say don't write it down? Because I promised you that after we had this first test, I would never make you do this formula again. You could just get it out of 1-bar stats, right? So you're welcome. So don't even need that formula. Let's see. I do need this guy, obviously. Hopefully most of you guys just know that formula by now, right? This was introduced in chapter 2, so you might as well put this one down too. Then, of course, you've got chapter 3, which is all the probability stuff. Yeah. Hopefully these will look familiar. So you can follow, if you have all your formula sheets, you can just kind of follow along, make sure you got them all written down. Please, dear God. Have you guys noticed this? That I write terribly bad? I don't know if you guys have noticed that. So it's on you to make sure that your formula is correct. So I would double check with like old handouts or the book or something. So there's all the probability kind of formulas all stacked together. That's chapter 3. Then we get to chapter 4, which is where we have the x, p of x tables. So this is where we have stuff like the mean is the sum of x, p, x, standard deviation. Then we get into binomial stuff. Good Lord, what is that? All right, so that's chapter 4. So you can organize this however you want to. But so these kind of go together, and then these go together. Okay. And again, it's not the right way to teach this. But when you're done with all the explanations and you've gone through the derivations and so forth, you can start to go, okay, so when the problem gives me a table with x and p of x, I'm going to use these formulas because they have x and p of x in them, right? So you can get to the nuts and bolts level of just which formula makes sense to use in which moment. These I use if I tell you a percentage of people do this, so there's a percentage of people that don't, and I have this many people, what's probably I get this many success? Okay, that's NPQX, that's that kind of problem. I call these NPQ problems. Okay, so that's chapter 4. Chapter 5 was uniform distributions, which I'm not going to be that concerned about, to be honest. In fact, I told you at the time that the mean and standard deviation, I just wanted you to be aware they existed, and then I really don't use them much, because they're really not used that much. Because you really don't run into uniform distributions that much in real life anyway. Then we get to chapter 6, which is basically this comes back, right? So you already got this stuff here, so then we can just go to chapter 7, which is where we do stuff like this. Chapter 7 is the central limit theorem, where we learn about if I take a sample and I take the means, I've got to change the spread, it gets skinnier, right? This is when we went to alternate universe Florida. We did our thing. Chapter 8 would be the confidence interval stuff. So you only use the plus or minus formulas when I ask you to make a confidence interval. It's the only time it makes sense to use them. There's only 3 formulas that have a plus or minus in them, and those are the confidence interval formulas. So you got this guy, you got this guy, you got this guy, and then you got these 3 comes along with this. So remember, the formulas tell you what the hell the idea is with Z and T, right? When do I use Z? When I know the population standard deviation and it's normal. When do I use T? It's normal and I only know the sample standard deviation. The formula tells you that. Okay. So that's chapter 8. Chapter 9 was everybody's new favorite thing, the hypothesis tests. And the only real new formula from chapter 9 was so you can put down here if you want to, Z star. It's the same formula as is over here, but you can do it again if you want to. I don't know why you would, but you can. But the new one was this one. For hypothesis test for percentages. And then chapter 10, I made extra credit. Chapter 12 was linear correlation stuff. There's no formulas for us to use. We just do it all in the calculator. Chapter 11 was chi-square stuff. So that's where you need this guy. And again, that formula is a lot like this formula in the sense that whatever it calculates fits in that chi-square distribution. So like whatever this calculates fits in the normal distribution. It's the same kind of idea. And no, this has nothing to do with Dragon Ball. Sorry. It's a different chi. I always like to say, see if I have any Dragon Ball things. Any formulas you think I missed? If you're looking at your old formula sheets, any formulas you think I missed? I'd be sort of surprised if I didn't, but maybe I got them all. Damn. Look at that. Wow. I'm not sure if anybody would agree with me. That's beautiful. Look at all that. That's beautiful. God, you're weird, Jeff. All right. So anything else you think you should be allowed to have besides these? Okay, so that's all you can have. These right here. Okay. So make sure you bring that formula sheet with you. So one way we could go forward today is obviously if anybody has specific questions, that comes first. If nobody has specific questions, I might start picking problems off the practice final for you guys to try. Like for example, it might be good to start with a linear correlation problem, considering we just had the quiz, right? Or a chi-square problem, especially if you weren't here for the chi-square stuff. Does anyone have any specific questions you want to start with? Number one?
Yeah, what should number one?
Yeah, number one is what I call the bread and butter of stats. It's the classic immediate stats problem, which is it's a normal distribution, right? We're assuming it is, yeah. And we know the mean and the standard deviation, so under the probability that randomly picks something is somewhere. So that's the old draw the picture, identify the mean and the standard, and the point you're interested in, make it into a z-score, that whole thing, look it up. Does everybody have all these? You all have this? Okay, make sure I got it all on here. Okay. So the question is number one. Can you guys just go ahead and look at number one? Try to set up 1A. Try to set it up. So we're assuming it's normal. Put the mean in the middle. What else do I want to put down there in my picture?
Arrow pointing to the right.
Well, is there something still missing? Arrow pointing to the right, starting where? What's the question? Probability that it's greater than 200.
Oh.
So where's 200? To the right. Just pick a spot, and then that's what I want. That area there, right? Now technically you don't need to draw the picture to be able to do the problem, but the people that make the most mistakes are the ones who don't draw the picture. It's a very simple mistake to make here. If you don't draw the picture, you're more likely to make it. Now, what's the very next step I do? So they told me it's normal, so I can draw that bell curve. They told me the mean. They told me the point that I'm interested in, and they told me which way to shade. Okay, so they gave me all this. I just had to put it together. Now what do I do? How do I find that probability? Do we have a sheet that has all the answers on it? for normal curve? Oh, okay. So what are you doing? You're making it a z-score, right? X minus the mean divided by 3850, the standard deviation. All right, so I try to do that. Let's see what we get. You're gonna get like 0.9 something. 917. See what you guys get. Make sure Sophia's right. Sophia says it's 0.917. And again, some of you guys still make the mistake. You gotta tell the poor calculator. It doesn't have eyeballs. You gotta tell it what the top is. Is anyone getting that? 917, is that what you got?
Yeah.
So what should I put then? 92, because the z-score chart only goes out 2 places. So the big mistake I see is, even if people draw the picture, I still get this mistake. What's the next step? Now we got that z-score, what's the next step? Sometimes, real quick, I'm sorry. This is a mistake I'll see. Somebody will write that down, and then they'll say the answer is 92%. Yay! Right? That's not a percentage though. That's a z-score. So tell yourself what the hell you're doing. This formula is z-score formula. That's just a poor little z-score dude. So I'm sorry, Daisy, what do you do next? Or anybody? Yeah, look up the z-score chart. Look up 0.92. Sorry? 8212. So is that the answer?
No.
Yay! No, damn. Because that's the area that's below there. So what's the area that I need? So what do I? Yeah. So 1 minus that. 0.1788. So about an 18% chance to find somebody who spent more than $200 on coffee in a year. Now this data is accurate, but I've used this practice final for quite a while, so I think this is accurate back in like 2006 or something. I'm pretty sure today it's probably way more than this. What's the difference between this one, 1A versus 2A? What's happening in part 2 of number 1? You see, part 2 says find if we selected 32 US adults, right? Taking a sample, so what's got to change? Standard deviation. So I'm taking a sample, I got a sample size 32, and I'm asking about the sample mean, so therefore I've got to change the standard deviation. I've got to figure out the new standard deviation. So if I ever take a sample and then ask a question about the sample mean, I need the frickin' standard deviation that works for groups. Not the one that works for individuals. This is how individuals are spread out. I need the one that works for how groups of 32 are spread out. By the way, I don't ask this on this, but I could have. Why in part 2 do I not need to assume it's normal? Part 1 I did. Why do I not need for part 2? Greater than 30. Sample size is bigger than 30. So I know it's normal enough. So I don't know, I could ask that question at some point. Intent. All right. So then this problem, you're gonna work it exactly the same way we did this. It's gonna be all the same damn work, except that number is not gonna be 3850. That's the old stuff. I need the new stuff. It's gonna be like 6.98. 805. 805?
Yeah.
I think most of you guys kind of get this, but you're just not sure when to do this. It is when I take a sample and I ask a question about the sample mean. That's when we do this. And now the work is all the same. It's all the same freaking work. The picture looks the same. The z-score formula is the same, except you put 6.805 here. It's like 0.15. It's probably not 0.15. It's probably, well, maybe it is. Somewhere around there. What is it? Oh, I went the wrong way. Good job, Jeff. Multiply. Yeah, 5 point, I would have said 5.5 something. So what is it? 9.8?
1.85.
5.19?
18.5. Oh, yeah.
Okay. You guys getting that same thing? Why does that make sense? Because when I take a sample, this whole thing gets skinnier, which means that this will be relatively further away. The step size got really small. So now 200 is much further away. It's more steps. So I really, the physical interpretation, if I'm standing at 164.71 and I want to walk to 200 and every step I take is 38.5, it's only going to take a few steps to get there. It's going to take, in fact, less than one step to get there. Now if I change my step size to be 7, roughly, and I start at this, and now my step size is, now it's going to take frickin' over 5 steps to get there. Now what the hell does that mean though? When you look this up in the chart, what do you get? Look up 5.19 in the chart. Poor little chart freaks out, yes? It only goes up to 3.5, right? So officially the chart says this is how much area below that. 9999, yeah. So then the answer would be 1 minus that. I would accept approximately 0%. Because we're way further than freaking 3.5 steps. We're 5 steps up. Holy shit. Really quick. The mean height of men was 69 inches with a standard deviation of 2.5, I think it is. What's 5 steps? 5 steps would be 5 times 2.5, which is something. 12.5? 5 steps is 12.5. Does that make sense, Jeff? I don't know what you're doing, buddy. Yeah, so that would mean a height of 12 plus 69, 81.5 inches tall. You guys with me? So that would be, well, let's see, why is that not that impressive? I don't know why not. Is that right? 5 times that is, yeah, 12.5.
That's right.
81.5 inches, which will be 5, 6. Let's put something, yeah. It's pretty damn tall. Okay. So anyway, so 5 steps away is really damn far away, which is why such a small percentage would be above that. So at this point, you should, if you get a z-score of like 4, 5, 6, you're like, whoa, holy shit. That's kind of crazy. A z-score of 0.92, that's not even one step, it's fine. 5.19, whoa, what the hell? We're 5 steps above the mean in this case. That's crazy. Okay. Okay. Number 2 is kind of like the probability problem on this practice final. I will tell you this. It's a very good chance that I would put like, remember the tables? That I would put like less than 20 years old, at least 20 years old, yes, no, right? You have to add them up and you can answer all these probability questions. So I really like those kind of problems. So it could give you a problem like that, or it could give you a problem like what's on the practice final. I don't know, I haven't really decided yet. So if you scan through this test really quickly, are there any problems that really don't sound familiar? Yes?
Can you go over 11?
Good, 11 I definitely want to do. So we'll do 11 and then I'll come back and see, really take a look and see if any don't sound familiar. Hello. Okay. So 11. Okay. If you weren't here last time, this is going to be difficult, but I want you guys, can we all try to do number 11? Can you guys get as far as you can with 11? And for some of you guys, as far as you can get is just kind of looking at it. If you haven't watched the video. But try to get as far as you can with this problem. You're going to need your chi-square table. Does anyone not have a chi-square table? Okay. Can anyone tell me what's the easiest part of this problem? What is the absolute easiest part of this problem? Say again? Yeah. I just tell you what the observed are, right? Just plot that shit on down. The expected is going to be a little bit freakier. By the way, what kind of distribution is this? Roughly. Starts at 13, goes to 20, goes to 34, back to 20, down to 13. Normal. It's actually the approximation to the normal curve for 4 categories of things. So there's this, you guys, before you took this class, you all heard about the bell curve, correct? And there's people that assume that things will all fall into a bell curve, which is actually absolute bullshit. But for this problem, I'm trying to see, do the grades that I observe actually follow a normal curve or not? Now, just by observation, do these look like they're roughly normal? Starts low, goes high, goes low again. Right? Now, it's not perfectly symmetric, so now the question is that close enough to normal or not? So whenever I'm saying normal enough, this is our first example of a test that will actually be more specific about if it's normal or not, instead of just kind of like looking at it. Can somebody help me? How would you figure out the expected number here? What do I have to do first?
Take the total.
Good. You gotta find the total of these. Has anyone done that? I think it's 342. Is that right? Okay. So how how would you figure out the expected number of A's?
342. So you do like 0.13 times.
Yeah, 13%, or what I expect for A's, so I would do 0.13 times 342. Now let me show you something. You could do this. This is kind of nice. My batteries are low. You can just go away. Real quick, I want to show you. So if I go to in tables and clear some stuff out, put into table 1, 53, 63, 131, 60, 35. Now watch. List 2, I want list 2 to be the expected. Well, okay, so that's 13% of 342. Bam, right? You just do all the calculations inside the table. Why the hell not, right? You with me? What am I going to do for the next row? How do we get the next thing?
120.
Yeah, that's B's. B's will be 20%, so I want 0.2 times 342. And then you get the C's, I would just do I would get the C's.
34.
Yeah, 34%. Point, Jeff, 0.34 times 342. And then the funny thing is, see how it's going to repeat here? It's the same thing, so I can just put 44.46 again. So in here, I can just go ahead and do 0.2 times 342, and where'd it go? 13 times 342. So I should get a nice boom, 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 boom. So that's perfectly normal. Shoot, did I put that in the wrong place? I did. Jeff. 68.4 and 44.46. How do I get list 3? What do I want the third list to be? Shit, I don't want that. I'll freak out. How do I get list 3? What do I want it to be? So this is list 1. This is list 2. So what do I want list 3 to equal?
List 1 minus list 2 squared.
Yeah, so it's exactly what I type in. I go up to L3, and then just type in parentheses L1 minus L2 squared. Bam! And then I copy all this shit down. Blah, 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 blah. What do I want L4 to be?
L3 minus L1. I mean L2.
Divided by
L3 divided by
L1 or L2.
L2, yeah. Divided by the expected. So I go to L4, make it L3 divided by L2. Shabam! Let me stop for a minute. So, I mean, that's... Those of you who are more exploratory might have discovered that there is a way to do, let me think, actually I can't remember it myself either. Chi-squared test and chi-square stuff in here, right? Chi-square test. Goodness of fit test, that's part B there. But maybe we'll take a look at that in a minute. So coming back to my table, what do I need? What's my chi-square gonna be? How do I calculate it? What do I do with that last row? The last column to get the chi? Just add them up? Yeah. And what's the quick way to add them up? I can do the old thing we used to do. Quit out of here, go to second stat to go to list. I want to do math on a list. I want to sum up a list. I want to sum up list 4. Bam. Now, how do I figure out what to compare that to? What did I not give you? That I actually didn't give you on purpose.
Alpha.
Alpha, I didn't give you alpha, so when I don't give you alpha, you assume that it's
Oh, 5.
05, that's just the most commonly used one. Can somebody remind me, what's the degrees of freedom for this? Is it 341? What's the degrees of freedom? You can take away, no problem, huh?
4.
Yeah, because there's 5 categories, so it's just one take away from the categories. So
9.
5 categories minus 1 is 4. Can you take a minute, look at your chi-square, don't say anything. Try to find the correct critical score, the correct rejection region. Whoa, shit. Oh. So alpha's 0.05, where did I get that from? Well, that's what I assume when I don't see one. Degrees of freedom is 4. So I get 9.488. So we have to be more than 9.488 to show evidence that it's not the same. Did we make it that far? Nope. There's our 6.975. So did we find sufficient evidence to say that this data does not follow the expected pattern? No. So what's a quick way to answer this? We have not found evidence that this data does not follow that pattern. So basically, we haven't disproven this is normally distributed. So it's a more technical way, instead of just kind of looking at it going, well, it goes up and then it comes down. So no, this is a more technical way to test. Is it normal? This kind of tells me, okay, it looks like I can assume this is normal. I can't prove it isn't normal, so I can kind of go forward as if it was. All right. Maybe. Now, to be really honest, I don't think I've ever freaking used the. That's one reason why I looked in here. I don't think I ever used this. No, I'm kind of curious how this thing works. Goodness of fit test. List 1, okay, list 1 is observed, list 2 is expected, degrees of freedom is 4. Sure, blue sounds good. Calculate. Does anything look familiar? There, chi-square. 6.97, isn't that what we got? 6.975? Yay! Here's what we can't get by hand. It actually gives me a p-value because it's a calculator, so it's a little better than for us humans, but there you go. That last part, don't worry about this last part, the CNTRB. Do not worry about that. Okay. But yeah, in fact, don't even worry about that at all. You don't have to know how to do that at all. Because we can do all this by ourselves and get the same answer. Go humans, right? Okay, maybe. So again, the purpose of this, the name goodness of fit is silly, but it's perfect because that's exactly what this thing does. Here's some observations I made. Does it fit with what I expected to see? Goodness of fit. Did what I see fit with what I expected to see? So if I make it far enough away, then I can say, no, it didn't. If I don't make it far enough away, I go, well, I haven't shown that it didn't. What's the only way to get 0 here, by the way? What's the only way to get 0? What would have to be true about these things here? They'd have to be perfectly equal. That's the only way that this would come out to be 0. You guys see that? The minute there's a difference at all, I'm going to square it, it's going to add, it's going to be bigger than 0. So the further I am away from 0, the more and more evidence it is that they're different. This is the hard line that's enough evidence, right? So in a criminal trial, if somebody's on trial for murder, could there be some evidence somebody committed a murder, but then they're found not guilty? Shit, yeah. Just not enough evidence has been shown, right? Not enough. So there's this idea of, okay, there's some evidence, just not enough. Okay. Maybe. Okay. Anything else on here you guys want to kind of do together? Obviously, I'm going to have the answer key for this next time anyway. So you can ask questions from other things too, from homework, from other tests, whatever. But is there anything there that you kind of want to go over Another option is to end for today, and then Thursday's another day of review anyway. And by that point, hopefully you guys have tried some of the final exam, the practice final stuff. So you'll have some more questions, right? So that's another option. And of course, on Thursday, I'll have the quizzes graded. So that's another thing you can do is do corrections. I'll have an updated grade sheet for you guys. It's gonna tell you, I can't remember the last grade sheet I gave you. Did it say what you need on the final to, what you need on, so now this is gonna say what you need on the final to pass, to make a B, all that kind of stuff. Right, so you kind of have some targets. Okay. So if you've had enough for today, that's plenty. We can head out and we'll pick it back up on Thursday. Please, God, don't forget your IDs. Don't like carrying these things around. Shoot me an email and I can send it to you. Yeah, so then you can work on, yeah, I can send you your scan and I can send you a blank copy if you wanted with quiz, with printout, try and do corrections or,
Yeah.
okay, so just put that in the email, I'll send it to you.
Thank you.
Sure. So you whenever you do a hypothesis test, you're assuming that the number from the claim is correct. So P is 0.19, which will make Q 0.9. I think you put that's the actual P hat, but I don't want it hat. P hat meaning a sample. I want the one that's the real percentage, and we're assuming it actually is 0.1. Oh, still recording. It's a really exciting part.
Is Sam homework?
Sweet.